In the second approach, let's try to use union find on prime factors. So in the above algorithm, we would enumerate through a series of non-essential factors for a number. For instance, for the number 12, we have a number of factors as 2, 3, 4, and 6. So in this case, the factors of 4 and 6 are not essential since they have been covered by the prime factors of 2 and 3. If there are another number, let's say 30, that has a common factor with the number 12, so then the common factor is either one of the prime factors 2 and 3 or 6, which can be further divided by these prime factors, right? This intuition is that the prime factors of a number can be represented all of its factors. For example, the integer can be characterized by a series of prime factors. Indeed, by the fundamental theorem of arithmetic, every positive integer has a unique prime factorization, and each positive integer, except one, can be decomposed into a series of prime numbers. For example, the 12 is equal to 2 multiplied by 2 multiplied by 3. With the above series, rather than enumerating all of the factors of a number, we just need to enumerate the prime factors of a number in our union find data structure. So here, we try to use a Sieve method before we proceeding to the main algorithm for this problem. Let's just briefly list the algorithm to decompose a number into a series of prime factors, which itself is not an easy problem. Here, we just apply the Sieve of Eratosthenes. Let's call it Sieve method for short, which is an ancient algorithm to calculate all of the prime factors up to any given limit. Let's try to decompose 210. 210 multiplied by 2 is 0, so the 2 is the prime factor. 210 floor divided by 2 is 105, and 105 is the num, so we use 105 multiplied by 2, which is 1, which is not equal to 0, so we have to increment the factor 2, which is become 3. 105 floor divided by 3 is 35, so the 35 is the num, and 35 modulus by 3 is 2, which is not equal to 0, so we try to increment the factor from 3 to 4. Now the factor is 4. 35 modulus by 4 is 3, which is not equal to 0. And then we increment the factor 4 by 1, which get 5. And 35 modular by 5, which get 0. So the 5 is also a prime factor. We just use 35 to 4 divided by 5, which gets 7. And 7 is our nums. So we have to finish it, because the square of the factor 5 is greater than number 7. So the nums variable changes from 210 to 105 to 35 and until 7. So we have to write 7 into our prime factor. The 2, 3, 5 are factors. We write them down in the prime factor list and also with the number 7. Let's try to decompose 16. So 16 modulus by 2 is 0. So 2 is our prime factor, and then we use 2 to floor divide 16, which get 8. 8 modulus by 2 is 0, so the prime factor 2 didn't change. We use 2 to floor divided by 8, which get 4. And 4 modulus by 2 is 0, and the factor 2 didn't change. We use 2 to floor divide 4, which get 2. It is our last num. So the nums variable changed from 16 to 8 to 4 until 2. And the factor is 2, 2, 2. So we write them down in the prime factor list, 2, 2, 2, 2. Let's consider the input when num is 19. In the first iteration, the factor is 2, but 19 modular by 2 is not equal to 0, so the factor will be increment to 3. And in the next iteration, the 19 modulus by 3 is not equal to 0, so we increment the factor to 4. In the next iteration, we increment the factor to 5, but 5 is greater than the square root of 19, so we terminate the while loop, and the prime factors of 19 is only one element, which is 19 itself. First, we define a function called prime decompose that will take an integer num as our input, and then we create an empty list prime factors that will store prime factors, and finally we have to return a list of prime factors. First, we set the factor to 2, which is the first prime number, and then we enter a while loop which continue as long as the num is greater than or equal to factor square, which means the factor should be less than or equal to the square root of the num. Within this loop, If num's modular by factor is 0, that means the factor is a divisor of the num, so we just append the factor to the prime factor and divide num by the factor so that we can find the next divisor. And if the num modulus by factor is not 0, then we just increment the factor by 1 and continue to our next iteration. And once the while loop is finished, the nums will become the last prime factor of the num. So we just append the num to the prime factors list, and finally we just return the list as our result.